Okay, let's go ahead and get started. Today I'm excited because I get to teach you about Newton's second law, which is the most useful of all the laws of classical physics. Now on Friday we'll talk about Newton's third law, which is the most beautiful, the most elegant, and the least understood, I think, of all of the laws in classical physics. So don't miss Friday. We're ready to do some homework, or we will be by the end of the day. In Chapter 5, problems 11, 13, and 16, before the end of the lecture, I'll work a problem that's similar to problem 11, by which I mean the same. Let's take some attendance here really quick, since we don't have homework to turn in. Okay. Whoop, whoop, whoop. Now? Okay. Last day we talked about our palette, if you will, of forces that we're going to use on all of the problems we deal with in the next 3 weeks. We have two non-contact forces, gravitational and magnetic. These are forces that can act over a distance. It doesn't have to be contact. The gravitational force is the first force you put on any free body diagram. Point straight down. We'll talk more about it later today. Then we ask ourselves, were there any magnets in the problem? Usually not, sometimes. But once you cover those two forces, all other forces have to be due to things that touch your object. So you just make a list of what touches my object. For each thing on that list, you ask, does it push or does it pull? If it's a chain or a thread or a string or a rope, it pulls. And for each one of those that touch your object, you get exactly one tension force. One. If it's not a string, it's not a thread, it's not a chain, it's not a rope, it pushes. And whenever one thing pushes on another, there will always be a normal force, by which we mean a perpendicular force. Not an ordinary force, but a perpendicular force. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. So for each of those things that are pushing, you get at least one force, at most two forces. And so you can follow that recipe and be sure that you get the correct free body diagram. Now, we talked about Newton's first law, which said that no net force gives me no acceleration, and no acceleration just means constant velocity. Now, the purpose of Newton's first law is to set the stage for the second law. If you're sitting in an airplane on the runway, just sitting there, and you take the tray down and take a rubber ball and put it on that tray, if the tray is level, the ball's just going to stay there, which is what you'd expect. If that plane is going 600 miles an hour and it's a smooth ride, if you're going a constant 600 miles an hour in a straight line, you can put that tray down and do the same experiment, and that ball will still just stay there. You don't know that you're not in your front room, okay? Both of those reference frames we call inertial, by which we mean there's no acceleration. And in an inertial reference frame, Newton's second law applies, okay? Now, you're not supposed to do this, but if you put your tray down while the plane is taking off, if you put that ball on the tray, it doesn't stay there. There's magical forces that make it race towards you, okay? And in that accelerated reference frame, you can't use Newton's second law and expect it to be valid without making up some fictitious forces, okay? So what we will be doing in this class is we'll always be doing our physics in inertial reference frames. Typically, we're going to do it in the frame of the sidewalk, okay? The sidewalk. Now, we did this trivial exercise, and we found a very non-trivial result. Any object that's moving has two vectors that describe that motion, the velocity and the acceleration. And it turns out that the force causes one of those vectors, but not the other. The force is always in the same direction as the acceleration because it causes the acceleration. It's sometimes in the same direction as the velocity, coincidence, okay, just by happenstance. But there are other times when it's not in the same direction as the velocity. Now, Newton's second law is that a net force causes acceleration. And by net force, we mean the vector sum of all the real forces. The example we took was a piece of dry ice that was accelerating down an inclined ramp made out of slate. We draw a free body diagram for that ice. The first force we put on any diagram is the weight force by the earth on the block. We then ask, are there any magnets in this problem? No. What touches the block, the ramp? Does it push or does it pull? It's not a string, it's not a thread, it's not a rope, it's not a chain, so it pushes. Whenever one thing pushes on another, there will always be a normal force, ramp on the block. And by normal, we mean perpendicular to this interface, this surface between the pusher, the ramp, and the pushee, the block. Now, the important point is it's not that force that causes the acceleration. It's not that force that causes the acceleration. It's the vector sum of all the forces. I've got to take the forces and add them as vectors. There's the plus sign. And the grand total we call the net force. Because that net force causes the acceleration has to be in the same direction, which in this case is down the ramp. Now I'm going to illustrate that with a little demo here. I have 3 jars of water, a piece of masonite, and I've also got some high-tech tubes. We spared no expense. This is your tuition money. And we've got some raw eggs. We're going to put the raw eggs on top of those tubes. And then what we're going to do is we're going to hit the masonite out from under the eggs. Are you ready? Some of you are thinking, surely he wouldn't use raw eggs. Surely he's not that dumb. You're wrong. I am. Okay. Now, as you've noticed, some seats are better than others. Actually, a little more controlled way to do this would be to just... Okay, now, let's talk about what just happened. When the broom handle hit this piece of masonite, it had a net force that way. If I look at all the forces acting on the masonite, I've got the weight down, I've got these jars pushing up, I've got these tubes pushing down, but all the up and all the down was balanced until it got hit with the broom. It had a net force of 0. And then that broom gave me an extra force, an unbalanced force in that direction. And that's what happened. It sped up in that direction. Now, once it got away from the broom handle, and once it got away from these jars, what does its free body diagram look like here? Yeah, just way down. And that's free fall. And things in free fall travel in that parabolic trajectory that we talked about in projectile motion. Now, let's look at the eggs. The eggs were just sitting there with zero velocity when suddenly those little tubes were just kind of lifted out from under them. Now, if you look at the free body diagram for the egg, it was simple. It just had a wave force, Earth on the egg. And that means the total force, or net force, if there's only one force, would be down. And that's what happened. They sped up like Wile E. Coyote, straight down into the water. Okay? Now, we noticed that the net force was nowhere on our chart because it's not a real force. It's a mathematical construct. It's the sum of all the real forces. Now, last day, at the end of class, we had you vote on this pretest question. You have this crate crashing through the snow. It's moving down, and it's slowing down. And it's a 50-pound crate, and you were asked, is the upward force by the snow greater than 50 pounds, equal to 50 pounds, or less than 50 pounds? You know the answer. We gave it to you on Monday. Let's just see if you remember. Let's see if you got your money's worth. If not, we'll give you a refund on your tuition. So, just send it in an envelope. Okay. Good. Good. We remember. And I hope we believe, okay, because this is what makes you Newtonian. People who are Newtonian have connected the force with the acceleration. In other words, they've learned to ignore this velocity vector that is oh so visual. Now, years ago, 23 years ago, when I came to teach here at Montana State, I was trying to convince my colleagues who were teaching the other intro classes that this was a problem, that many beginning students misunderstand that force is causing acceleration instead of velocity. One of my colleagues said, "Oh, my students don't have that problem. My students are the calculus-based students. My students had high school physics. They're fine." So I kept on hammering on him, and finally he relented, and he gave this pretest. And he was just astounded at how many students got it wrong. But what really convinced him is his best student ended up in his office just spitting mad. But it's still going down. So what? That's what you have to ignore. So what? That's not important. The important thing is it's slowing down. And that acceleration vector is what is caused by this force diagram. This diagram has to scream that acceleration. If that's up, this has to scream up. And today's lecture is all about that scream. How loud is that scream? That's the question that's answered by Newton's second law. Newton's second law. Now, to understand that, we first of all have to understand a concept called mass. How many of you have dealt with this in an earlier class, like the 4th grade? Okay. What did they tell you mass was? What's mass? Anyone? Brave soul?
The downward force on an object by gravity.
The downward force by gravity? That's not what I think of when I think of mass. What do they teach you typically?
It's the amount of matter something.
The amount of matter that something has. How much stuff something has. And that's pretty much the definition that you get in most classes. Now I'm going to need some help from you three. Thank you very much for volunteering. Come on down. I have some objects here. If you each face the class and hold out both hands. Your name, sir, again?
Barrett.
Barrett. Okay, one of each. And
Jackie.
Jackie? Courtney. Okay. Now, I've given each of these individuals 2 objects, and I'm going to give them exactly 20 seconds to figure out which of these 2 objects has the greater mass. They can do anything they want to figure that out. Da 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 da. Okay, we're out of time. Okay, Barrett. This one here, okay? Which one?
This one, it feels heavier.
Okay, it feels heavier. They're equal. Okay, let's give them a hand, folks. Okay. Now, the answer is, I don't know. I chose these 2 objects because they're pretty close to each other in mass. What I cared about was how they determined which had the greater mass. Now, for part of the time, they were holding them, and I'm going to try to get into their heads and think of what they were thinking. I'm thinking they were trying to measure which one was pushing down on the palm the most, which one was being pulled by the earth the most. And that's what we call the weight, okay? That's the weight force. Now, at one point, each of them did this, or this, okay? They did a better job of catching it. They sped it up. They shook it. And that is what a physicist thinks of when they think of mass, is how hard is it to accelerate it? How hard is it to speed it up, to slow it down, to shake it? To shake it. Now, the important thing to know is that that is very, very different than the weight. Now, it is true that here on Earth, things that have a lot of mass weigh a lot. But we have to be a little bit more global in our thinking. We have to be willing to leave home, okay? If I had an anvil, a great big heavy anvil, and I was holding it in my hands, it would push down really hard on my palms. I'd have to be Arnold Schwarzenegger to do this. If I took that anvil and I shook it, it would be really, really hard to shake. Now, if I take that anvil to the moon, where the gravitational field strength is 1/6 as big, it feels like I got stronger. It only weighs 1/6 what it did on the Earth. It's not pushing down on my palms nearly as hard. But if I take that anvil and try to shake it, it's every bit as hard to shake on the moon as it is on Earth. That's the mass. Now, if I were to take that anvil into deep outer space, far away from any planets, it'd just hover there. I could put my palm under it or not, okay? But if I were to anchor myself somehow and try to shake that, it would be just as hard in deep outer space as here on Earth. The mass is the same everywhere. And it's very different than weight. One story. I have a son who got his bachelor's in physics, made me very, very proud. And then he went to the dark side and got an MBA and started a business. But when he was in middle school here in Bozeman, we got a call from the principal asking my wife and I to come down and talk about our son. Now, we were surprised because our son was never in trouble. Never in trouble. And so we get there, and we walk in, and there's the science teacher. And he's mad. And I said, well, what's the problem? So I was trying to give my lecture, and your son went ballistic. I said, well, what was the lesson about? I was trying to teach those students that weight and mass are the same thing, and he exploded. He just started saying, are not, are not. And I looked at him and I said, are not? He said, of course they are not. And then he said, I'm the science teacher. I said, Trump, I wrote the book. I was ticked. I was ticked at him. I just said, how could you teach science and not know the difference between these two basic concepts? I wanted that principal to fire that guy. And then I cooled down. I apologized to the guy the next week. But I went home and I just grabbed my son and hugged him. I said, oh, I love you. Okay. So we're going to demonstrate this idea of weight with a demo that I call the hammer of death. Your name, sir?
Brandon.
Brandon, come help me out here. I need you to sit right here on this stool. And what I've got here is the hammer of death and a nail and a board. And what we're going to do, face the class there so you can see the pain. We're going to nail this hammer, or this nail, into the board. Now, Brandon, I'm fully insured, so I'm going to sit on that, and you're going to be up here swinging the hammer. So be careful getting up. Just stand up here. You'll be fine.
Are you sure?
No. Give it a try. Worst that can happen, what?
A little break.
Yeah. Now, what we're going to do is I'm going to sit here and I'm going to put this book here, and Brandon's going to hammer in that nail. Go ahead, Brandon. Try to be careful and not fall down.
Actually.
Good job. Now, stay up there. What is protecting my head?
The book.
Yeah, the book. What is it about the book that's protecting my head?
Mass.
Are you sure it's the mass? It's pretty squishy. Maybe it's just got a lot of give. Maybe it's a squishy that's protecting me. I got an idea. Let's get rid of the squishy. I have here a lead brick. Now there's no squishy in lead. Go ahead, Brandon. Okay. Now, what's protecting me there? The mass of the lead brick? Well, there's some squishy in that board. It's got some give. Let's get rid of that and see if it's really the mass. Okay, Brandon. You'll be fine. Okay. Okay. Keep going. Okay. Thank you. Okay, let's give him a hand, folks. Now, we got rid of all the squishy except for this right here. Clearly the only thing that was protecting me was the mass of this lead brick. Because it's so massive, it doesn't like to speed up or slow down. To hurt me, it's got to speed up into my head. And it didn't want to. And that made all the difference. Now, I'm going to do a demo here that I find more terrifying than the hammer of death. I call it the picnic of death. You've all wanted to do this at a fancy restaurant.
Oh no.
Yeah. I have an older colleague who actually tried this at a very fancy restaurant to show off the physics. Unfortunately, he was very drunk at the time. It did not go well. Okay. Now, let's see. We got this. Okay, people. Fork on the left or the right? Okay. So, let's see. Oh, okay. we need some wine. Fix that. Not bad for a Mormon boy. Trust the force, Okay. Now we're going to do that again. We would do that the way a student would do that. Because you are students, and because we are stealing so much money from you in tuition, you would use paper. Okay? That's a crime. That you people who are healthy and could travel the world and do all sorts of fun things don't have the money to do it. And people that are old and tired and all we want to do is watch TV, we got all sorts of money and I don't know what we should do tonight. We should just watch TV again. Okay, we should give all the money to you is what I'm saying.
Yes.
Yeah.
Totally agree.
Okay, now it turns out when you're using plastic, it doesn't matter what side you put it on. Okay, we'll put some of these things on here. Put these things on there. Now, I'm going to do this experiment again. And what I'd like you to do is predict, tell your neighbor what's going to happen when I do this again. Are you ready? Am I ready? Okay. The things with a lot of mass didn't want to speed up, so they stayed. The things that had very little mass, it was easy to speed them up, and so they took off, they accelerated off the table. Okay. Now, let's use what we learned about mass. During the summers, I teach courses for high school teachers. They come from all over the country, and we've had people come in from other countries. And during those classes, we make them build the physics from the ground up in a very careful way. And we do some detailed experiments. One of the experiments we do, two of them actually, is about Newton's second law. What they do is they take a mass and they exert a force on it. Now, because teachers have very low budgets, they don't have much money to spend, we teach them how to make force probes that have, it's just a meter stick with a long rubber band on it. And the stretch of the rubber band is proportional to the force. We find that that object accelerates. Then they take that same object and they exert twice the force on it. They find that the object accelerates by a greater amount. When they do careful measurements, they find out that the acceleration is twice as greater, if that's grammatical. Okay? So what they find is that acceleration, fish, net force. It's proportional. If you double that, you double that. Okay? Now the next experiment they do, they start with the original, the mass being pulled by the force. They find the acceleration. And this time, instead of doubling the force, they double the mass, the amount of stuff. And what they find is that the acceleration gets smaller. Indeed, with careful measurements, they find that it gets half as big as it was before. So that tells us that the acceleration is inversely proportional to the mass. Now, if we take those two experiments that I wish we had time to do with you, but we do not, you'll just have to take my word for it. If we put those experiments together, we get this relationship. The acceleration is directly proportional to the net force, and inversely proportional to the mass. Anytime I have a proportionality, I can replace that with an equal sign, provided that I include a constant. That proportionality symbol doesn't mean that the right is equal to the left. It just means that if I double the right, I double the left. So I have to put a constant of proportionality in there. Now, that constant, the size of that constant depends on which units I'm using. I've already defined my units for acceleration. That's meters per second for each second. It turns out that the units of mass are defined in terms of kilograms, where a gram is the mass of 1 centimeter cubed of water. We'll talk about that down the road a little bit. But that's been fixed. The thing that we can play with here are the units of force. Now in our country, in America, we use units of pounds. But we are the only nation on earth that does so. Everyone else has chosen to use newtons. And the newton is just the right size to make that constant equal to 1. And that makes the equation so much simpler. The equation then looks like that. And we call that Newton's second law. Now, the way you read that, the way I would like you to read that is a net force causes a mass to accelerate. But this also, the equal sign also means the value on the right has to equal the value on the left. And this gives us the answer to that question, how loud does my force diagram scream? How big is my net force? Well, it's mass times acceleration. Now, we're almost there. We just need one more idea. If I were to take 1 kilogram and hang it on this spring scale that measures force in newtons, what would the reading be? Anyone know? Why would you? We haven't done it before. Let's do it. I put that on there, and the reading is 10 newtons. Okay? So 10 newtons. Now, this you ought to be able to do. If I were to hang 2 kilograms from that spring scale, what would the reading be? 20 newtons. Okay? 20 newtons. And indeed, I can show that that's the case. I'll just hang this one along with the first. And sure enough, 20 newtons. Now if I did 3 kilograms, it would be 30. And indeed, any amount of kilograms I could just multiply by 10. Now, let's be sure that we know what we're measuring. That spring scale is measuring how hard we're pulling down on the hook at the bottom of it. Now we're going to learn on Friday that by third law, that's equal to how hard the hook is pulling up on the masses, the gold masses. That's this force here. The tension by the scale on the, it was a crate in the picture, we'll call it the masses. Now, indirectly, we're measuring also the weight, because that force has to equal that force. Why? Tell your neighbor why. That upward force has to equal that downward force. Okay. If you said by third law, slap yourself and don't miss Friday. Okay? Those two forces have to be equal to each other because those masses are not accelerating. They got zero acceleration. And if I plug 0 in for the acceleration, that means the net force has to be 0. That means all the force up has to balance all the force down. I've only got one up and one down. They have to be equal. What I'm getting at is that we can measure the weight force or we can get an expression for it rather, by just taking the mass in kilograms and saying the Earth pulls 10 newtons for each kilogram. Okay? It turns out that when you're on the moon pulls less than that, 1.67 newtons for each kilogram. Okay? Now I have a question for you. If Greg jumps off the physics building in a vacuum, what will his acceleration be? You know the answer, it's 9.8 meters per second down. We're going to call it 10. But let's solve this problem a different way. Let's use Newton's second law. Now the first step in any dynamics problem is to draw a free body diagram. Once Greg leaves the edge of the building in a vacuum, the Earth is pulling down on him with that gravitational force. There's no magnets around. Well, in this building there would be. Anyway, assume there aren't. Then there's nothing touching me. So that's my free body diagram. Now folks, when I use Newton's second law, the net force is the vector sum of all the forces on my diagram. If I've only got one, that is my net force. It's like saying, what's your net worth if you've only got one bank account? That's your net worth, okay? So I can plug that in, and we just learned that the weight was equal to the mass times this number, 10 newtons for each kilogram. So I'm going to replace the weight with that. And folks, here's the magic. The mass cancels out. So it doesn't matter whether you throw Greg off the top of the physics building or whether you throw a grand piano off the top of the physics building, it's going to have an acceleration of, well, it says 10 there, but that's only because I was using a pretty rough scale. If we had a very, very sensitive scale there, this reading, when I had 1 kilogram on it, would be 9.81 newtons for each kilogram. Okay? It turns out that this value, 10 newtons for each kilogram, is just G. Now, sometimes we call it the gravitational acceleration. Sometimes we call it the gravitational field strength. When we're worried about how hard the Earth is pulling on something, we call it the gravitational field strength, and we say the weight is just m times g. Now let me show you that the units work out just fine. The gravitational field strength is 9.8 newtons for each kilogram. But a newton is the force required to take 1 kilogram and accelerate it by 1 meter per second squared. And if I divide that by kilograms, I get 9.8 meters per second per second. Now, like I said, when we're worried about how hard the Earth is pulling down on something, we use this notation here, how hard it pulls on each kilogram. When we're looking at the motion of something that's been dropped, we write it this way, and we call it the gravitational acceleration. Check that your neighbor's on the bus, people. I've got a quick question. Is a newton a big unit or a little newton? Is a newton a whole lot of force or a little bit of force? Yeah. A newton is just enough force to take 1 kilogram and in 1 second, 1/1000, get it up to the speed of 1 meter per second. And it turns out it's not very big. I can help you to visualize how big it is. Imagine that after class you go to McDonald's and you order a quarter pounder with cheese. And then you get to your table and you take off the bun, you take off the cheese, you scrape off the secret sauce, and put the patty, the greasy patty, in your palm. that push down on your palm by that greasy patty is about 1 Newton. It's about 1/5 of a pound. And if you bought a 1/4 pounder thinking you were going to get a 1/4 pound of meat, you're silly. Okay? Now, let me show you how to work problems with this. When I was young, I would watch Star Trek. That should not surprise you. This was the original Star Trek where they had all the cheap props. It amazed me that they would go throughout the universe to all these different cultures and everybody spoke English. You know, it seemed too much of a coincidence. And I was ready to give up on the program until someone explained to me that they had a universal translator built right into their little medallion there. And then it was fine. Then I just, oh, okay, well that makes sense. The second law is the translator between kinematics and dynamics. It's the connection between the motion, and by that I mean the acceleration, and the forces, the free body diagram. Let me show you how that works. If I have a 5 kilogram mass being pulled by a rope with a tension force of 100 newtons, and I find that the acceleration that results is 4 meters per second every second, and I ask you, how big is the friction force? Well, in this case, I'm giving you the acceleration, the kinematics, and I'm asking you about the forces. The first step, folks, I got good news. I have students all the time coming into my office. I don't know where to start on this problem. And a lot of times that's a valid thing to say. But not with a dynamics problem, not with a force problem. Never come into my office and say, I don't know how to start this problem. Every single force problem starts exactly the same way. What? Free body diagram. Free body diagram. Okay? So let's draw a free body diagram. The first force I put on any diagram is the weight force. Straight down. Earth on the block. Now this is a 5 kilogram block. The Earth pulls on every kilogram 10 newtons worth. How many newtons is that pulling down on that block? 50 newtons. 10 per each. Okay? Then I ask myself, follow the recipe, ask myself, are there any magnets in this problem? No, not yet. Greg will get to it. So what touches the block? Well, the rope, and it pulls. So I get one force, period. The only thing other than the rope that's touching the block is the floor. It's not a rope, it's not a thread, it's not a chain. It pushes. Whenever one thing pushes on another, I always have a normal force. I may also have a friction force. In this case, I'm looking for how big that is, so I assume it's there. Now, just like the first step of every force problem is always the same, so is the next step. Every time you finish a free body diagram, you get to use Newton's second law twice. Once in the y direction, once in the x direction. Well, let's do it first in the y direction. That's the acceleration. How much of that vector is in the y direction, the up and down direction? None of it. And so if I come over here and do this in the y direction, that's 0. And that means in the y direction, my diagram has to scream balance, 0. I have to have just as much force up as down. That tells me the normal force is 50 newtons. Now in the x direction, it's not balanced. This force is bigger than that force because the diagram's got to scream that acceleration. Okay? Well, the question is, how loud should it scream to the right? How loud should it scream? And that is answered by Newton's second law. The scream has to cause a 5 kilogram mass to accelerate at 4 meters per second squared. The scream has to equal 5 times 4. The scream has to be 20 newtons to the right. Now that doesn't mean that this rightward force is 20 newtons. It's not, it's 100. That means I've got to have 20 more newtons to the right than I've got to the left. What's this friction? 80. 80. Now that's the way I solve problems. Now some people don't like to do it that way. They don't want to talk about the scream or they use their gut. They'd rather use math. So let's do that. The net force is just the sum of all the forces. You add them up. And since I'm doing it in the x direction, I add up the forces that are in the x direction. Well, Greg, your mouth says you're adding them, but your PowerPoint says you're subtracting them. No, it doesn't. I'm adding them as vectors. And because this one's to the right, I add it as a positive number. Because this one's to the left, I add it as a negative. Okay, so I'm adding the vectors as I would add, I'm adding the forces as I would add vectors. Because they are vectors. Now if I just plug and chug, 100 minus f is equal to 5 times 4. You just grind away at that algebra and you get the same answer that we got, 80. Okay? Now, if that seems trivial, it's because it is trivial. And I wish that I could say it's going to get harder. Because they'd pay me more. But that's it. That's Newton's second law. We're going to do that with problems that look messier. We're going to do that with problems that have more complicated algebra. But we're always going to be working that problem right there. Now, here's your homework. It's like your homework. In your homework, you have a sled that has a mass of 30 kilograms. This one has 15 kilograms. You can fix it. If we pull on this sled with a rope with 100 newtons at 37 degrees, and we know that the friction force is 50 newtons, in this problem we're asked to find all the other forces acting on the sled and find the acceleration of the sled. Now I want you to appreciate something. Last time I gave you the acceleration and asked you to find the forces. This time I tell you enough about the forces that you can find the acceleration. You can use that translator both ways. Now, the first step is to draw a free body diagram. The first force I put on any diagram is the weight. It's 15 kilograms. How big is the weight? I can wait. 150 newtons. And then ask, are there any magnets? No. What touches the sled? The rope, and it pulls. The snow, and it pushes with a normal force and a friction force. Now, the only difference between this problem and the last problem is that when I break up my problem into an x part and a y part, to use Newton's second law, I can't put that anywhere. That's not in the x direction and it's not in the y direction. So I have to break it up into its components. It's 37 degrees, a 3, 4, 5 triangle, so that's 3 times 20, 4 times 20, 5 times 20, or 60 and 80. Now folks, once you break up a force into its components, throw away the original. Use the components. Now, that's the first step. The second step is I get to use Newton's second law twice. In the y direction, I have no acceleration. It's speeding up to the right, so the y part of the acceleration is 0. That means in the vertical direction, this diagram has to scream balanced. How big is this normal force? And do not say 150. 90. I've got 2 forces up, I got 1 force down. These 2 forces up have to balance the 150 down. That one's 60, this one has to be 90. Now, in the x direction, I have 80 newtons to the right. I have 50 newtons to the left. What's the net force? What's the scream? 30 to the right. I got 30 more to the right than I've got to the left. If I use Newton's second law, 30 is equal to 15 times A. A's got to be 2. Or if I just plug and chug, I get 2 meters per second per second. Now, your problem's going to be slightly different than that, but the idea is the same. We've run out of time. Don't miss Friday. It's the best.